Swayam Prabha. Digital India. Educated India.
Welcome to the chapter on the ARM assembly language. ARM assembly languages are some of the most popular and most exciting assembly languages to learn. So in this chapter we'll have a lot of fun. So this chapter is a part of the book Computer Organization and Architecture, published by myself, Dr. Smriti Sarangi. It was published by McGraw-Hill in the year 2015 and should be available in almost all bookstores and online, both normal bookstores and online bookstores. So, why study the ARM instruction set? And so let's first look at why study and then what's the background required. So, ARM is a very popular instruction set. So, almost all the phones today, as of 2016, tablets and all kinds of small computing devices, which are not desktops or laptops, run on ARM processors. So they use the ARM instruction set. So ARM is a company located in Cambridge, UK. So they actually license their designs, and then the designs are used by other manufacturers to incorporate them in silicon chips. So before actually we start this chapter, I would like to make a point that readers should already have a good understanding of assembly language, in the sense that they should have read the previous chapter, which is chapter 3, and understood a lot of things about how assembly programs are written, how assembly instructions work, the notion of functions, the notion of the stack, the notion of encoding. So all of this needs to be there. And the reason that the book has been designed in such a way is basically that if it is not possible, at least in my view, to give an introduction to assembly language and teach an advanced assembly language at the same time. It is better to separate the concerns. So it is better to first teach what an assembly language is like, a very simple one, and then move to teaching an advanced assembly language which is used in commercial processors, because then a student would have the right amount of understanding to actually understand what a state-of-the-art assembly instruction set looks like. So keeping this in mind, I will actually start this chapter at a slightly higher level, because my assumption is that readers are already coming after read chapter 3. So they understand the basics of assembly languages, and they also understand how to write simple programs with assembly languages, and have a basic understanding of how to implement if statements, loops, functions, using stacks, using assembly language. So these are some of the concepts we'll take for given in this particular chapter. So coming back to ARM, so ARM has a lot of licensees all over the world. So what ARM produces is they create the design of a processor, and then they sell the design. The design can be incorporated by a third party with other components. So for example, if ARM sells a processor to a phone company, then they can incorporate the ARM processor and also have other smaller circuits around it. For example, a circuit to process inputs from the camera, or a circuit to interface with the accelerometer in the phone. So all of these additional circuits can be added. So the ARM instruction set as such is very versatile. So along with a lot of integer instructions, it supports floating point instructions, and it has what are called vector extensions. So we'll discuss more about vector instructions in chapter 11. But vector instructions allow us to do multiple additions at the same time in the same cycle. So we'll not be discussing these extensions. Also, ARM has a very popular, I would say, an assembly sub-language or an extension. It's called the thumb instruction set. And a lot of ARM programs actually use the thumb instruction set, which is a slightly simpler set of instructions than what we present here in in this chapter. So I can refer to it as the thumb ISA or the thumb assembly languages. So basically the thumb instruction set is similar to this. It's slightly simpler. We'll not discuss this in this chapter. We'll discuss the generic ARM instruction set for integers only in this chapter. So we'll have 5 separate sections here. We'll first start with basic instructions, move to advanced instructions, then look at branch instructions, memory instructions, load store kind of instructions, and finally consider instruction encoding. So similar to simple RISC, ARM has 16 registers. They are numbered from R0 to R15. And unlike simple RISC and many other assembly languages, the program counter is explicitly visible, and the program counter can be used to affect branches and so on. So this is exposed to software, is exposed to the assembly language. The memory is standard von Neumann architecture. What this means is that the instruction memory and the data memory is fused to one. So this is a typical facet of the von Neumann architecture, that there is one view of memory, it's not separate. So out of the 16 registers that ARM has, some of them are reserved for special purposes. So let's take a look at them. So R15 is the program counter. So I'm starting backwards. R15 is the program counter, so it's referred to as either R15 or the PC. R14 is the link register. You can also think of it as the return address register. R13 is reserved for keeping the stack pointer, or SP. R11 and R12 R11 and R12 can be assigned a special connotation sometimes. So R12 is an intra procedure called scratch register, which basically means it can explicitly be used to save temporary values inside a function call, but other registers can be used as well. And R11 is called a frame pointer. So we'll discuss what is a frame pointer actually towards the end of this chapter, but we'll discuss more about a frame pointer in the next chapter on x86 assembly. So we will be using a slightly different kind of semantics in this chapter. So every single instruction will be explained with the help of a table. So in the table, the first column will look at the semantics, which is something that we introduced towards the end of the last chapter. So it will basically show what are the different modes of the instruction. Then we'll give an example, and then we'll talk about the explanation in the register transfer notation that we have introduced. So the simplest of simple instructions in the ARM ISA is the move instruction. So what does the move instruction do? The move instruction transfers a value into a register. So let's say maybe move R1, R2. So it essentially transfers the value of R2 to R1. Alternatively, the move instruction can transfer the value of an immediate into a register. So the first operand is always a register. The second operand can either be a register or an immediate. So let's consider the second example, move R1. So here is a idiosyncrasy of the ARM ISA, that all immediates are preceded with a hash. So the moment we add this hash character over here, So you can see the hash character will be above 3 on your keyboard. So all immediates in ARM need to be preceded or prefixed with a hash. So when we say move R1 hash 3, what this essentially moves is that I take register R1 and I move 3 to it. So this is the simplest instruction in the ARM ISA. So move has a variant, it's called MVN. MVN is move not. So this is similar to the not instruction in simple RISC. So what we do is that when we do MVN R1 comma R2, essentially the ones complement or every single bit flipped is transferred from R2 to R1. So this tilde sign is the ones complement. So just to recapitulate, the ones complement of 1 0 0 0 in Boolean is 0 1 1 1. So every single bit is replaced with its complement. 1 is replaced with 0 and 0 is replaced with 1. So the MVN instruction is essentially the same as the move instruction, but instead of moving the register or the immediate, it moves in the complement of the register or immediate. So now let's take a look at arithmetic instructions. The arithmetic instructions are almost, the add and sub are exactly the same as simple RISC. So in this case, the add and sub instructions, similar to simple RISC, the first operand is the destination. The second operand is the first registered source, which is RS1. Recall chapter 3, and the second operand can either be a register or an immediate. So an example would be add R1, R2, R3. So in this case we add R2 plus R3 and save the result in R1. So again, I would like to mention that I'm deliberately going slightly fast because my assumption is that students have already picked up a certain amount of background in the previous chapter. So they will find covering this chapter slightly easier, right? But if you, let's say, take a look at this chapter from scratch, you will find it slightly difficult. So I would then ask you to look at the lectures or read the book for the previous chapter, which is chapter 3. So coming back to the add instruction, I can alternatively write add R1, R2 and hash 3. So what this would do is that in R1 it would save R2 plus 3. Similarly, we have the subtract instruction, which is exactly the same as it was in the simple RISC instruction set. So we have the register destination first. So the first operand over here is the register destination. Then we have two source operands. One of them is a registered source and the other is a source slash immediate, source or an immediate. So when I write sub R1, R2, R3, essentially inside R1 we are having placing R2 minus R3. So similar to subtract, there is another instruction, it's called RSB or reverse subtract. So in reverse subtract, instead of subtracting R2 and R3, instead of doing R2 minus R3, we actually do R3 minus R2. So here a reader can ask, if you have the sub instruction, why you need a reverse subtract instruction, right? Well, the answer is simple in the sense, let's say that you want to compute 3 minus R1, not R1 minus 3, 3 minus R1. We cannot write an instruction of the form. So let's say you want to set this to R2. We cannot write an instruction of the form R2 right. So this is not allowed because the second operand has to be a register. So this is not allowed, but what we can write is RSP or reverse subtract. Oops, sorry, there shouldn't be a comma here. R2, R1 and 3. So what this would do is this would set R2 to 3 minus R1, which is exactly what we needed. So in simple RISC, doing this would actually require two instructions, because we would first subtract 3 from R1, so compute R1 minus 3 and then multiply it with minus 1. So the designers in ARM are very smart. Instead of having this two instruction solution, they created a new instruction called RSP reverse subtract, which allows us to compute 3 minus R1 in a single instruction. Alright, so now let's take a look at some examples. So the first example is write an ARM assembly program to compute 4 plus 5 minus 19 and save the result in R1. So here is a simple solution which is simple, but it's not optimal, but nevertheless let's take a look at it. So we first save 4 in R1, we save 5 in R2 using the move instruction. Then we add R1 plus R2, save it in R3. We move 19 to R4. Then we subtract 19 from R3, which is R1 plus R2, and save the result in R1. A slightly more better solution, which is optimal, we put 4 in R1, then we do R1 equals R1 plus 5, in the sense R1 will become 9. Then we do R1, we set R1 to R1 minus 19, and the previous value of R1 is 4 plus 5, 9. So we compute 9 minus 19 as minus 10, which is the final answer. So this was a slower solution, easy to understand. This is slightly difficult to understand, but not very difficult, because in the first line we set R1 to 4. In the second line we do R1 is R1 plus 5, which all of you can verify is what is exactly mentioned in the statement of the problem. Then we subtract 19 from the sum and we get the right answer. Now let's take a look at logical instructions. So logical instructions are also very similar to the arithmetic instructions. So the first three instructions are somewhat easy. The fourth instruction is slightly difficult. So the first instruction is the AND instruction, which is very similar to what we had with simple RISC. In the AND instruction is the same idea, that so in all of these instructions, the first operand is the destination. Then we have the first source and the second source. The second source operand can either be a register or an immediate. So one example would be AND R1, R2, R3, where we set R1 as R2 and R3. So EOR is actually exclusive OR, XOR or XOR as we call it. So in EOR R1, R2, R3, we have R1, which is being set to R2 XOR R3. ORR is logical OR. So in a logical OR, what we do is that this is similar to the OR instruction in simple RISC. So we just compute a logical OR of R2 and R3. So the important point to note is that in all of these instructions, the instruction per se is only 3 letters. So in simple RISC, we had some 2-letter instructions like OR and so on. So that's not the case, and LD and ST. So that is not the case in ARM. So in ARM, they have tried to maintain the length of the instruction the same. So that's the reason OR they have replaced with ORR. So the BIC, the bit clear instruction, is slightly unclear at the moment. So what this is basically R1 is R2 and not of R3. So let's maybe consider a simple example and see what is this. So let's consider R2 being, let's maybe just consider 4 bits to make our life easy, and the rest of the bits are all 0. And similarly let R3 be So naught of this quantity would be 1 1 0 1. Now this number and this number is equal to 1 and 0 is 0, 1 and 1 is 1, 1 and 0 is 0, 1 and 1 is 1. See, if you see, what is happening over here is that all the bits that are set in R3, so all the bits that are 1 in R3, in naught of R3, those bits become 0, and when that is ANDed with some other quantity, all the bits at those bit positions become 0. So that's where the name bit clear comes from. So, or alternatively, if I want to explain, if this is, let's say, the first operand, which in this example is R2, and this is the second operand, which is R3, all the bits that are set at different points at similar bit positions in the final result, we have zeros. So it's like those bits at those bit positions are getting cleared. So this is called a bit clear instruction or a BIC instruction. So let's again consider an example, this time with Boolean variables. So write an ARM assembly program to compute A or B, the entire thing not, where A and B are 1-bit Boolean values. Assume that A is 0 and B is 1. Save the result in R0. So to compute the not of A or B, what we do is that, so basically ARM accepts hexadecimal numbers as well. So the format is the same. First have a hash to signify an immediate, and then you write 0x to signify that it's in hex. So what we do is that we load the value of 0 into R0, and we load, we OR this with 1. So the value of A or B at the moment is saved in R0. Subsequently, what we do is we compute the not of R0 using the MVN instruction. So we set R0 as the not of R0. So in this case, what we are doing is that we are loading two Boolean variables with constants. We are computing their OR, and then finally taking their logical complement. Let us now look at the multiplication instructions that are there in the ARM ISA. So the simplest variant of the multiplication instruction that we have in ARM is mul, MUL. So the mul instruction is very similar to the add and subtract instructions, where the first operand is a destination register. Henceforth, we have two operands. The first source operand is always a register, and the second one can be a register or immediate. So this is straightforward. R1 is R2 times R3. So even though ARM is a RISC instruction set, it has some slightly complicated instructions. And so, there is a basic trade-off. The trade-off is, do we always prefer simplicity? Or occasionally, can we make our instruction set slightly complicated, such that some commonly executing patterns in programs can be accommodated? So one such commonly executing pattern, which is there in a lot of programs, particularly codes that use linear algebra and matrix operations, is the MLA operation, the multiply and accumulate. So this actually takes 4 registers as operands. The first register is the destination. So in this example, R1 is the destination. So out of the 3 source operands that we have, what we compute is R2 times R3 plus R4. So we have a multiplication operation where the first and second source operands are being multiplied, and we are adding this with R4. So this is typically required in a lot of linear algebra kind of computations. That's the reason this instruction is supported. The other interesting aspect of multiplying two numbers is like this. So consider a 32-bit instruction set. So the range of the number system is pretty much between minus 2 to the power 31 to 2 raised to the power 31 minus 1. So let's say we multiply minus 2 to the power 31 with minus 2 to the power 31. The answer will be 2 to the power 62, which is well outside the range of a 32-bit number system. And so as a result, we'll have an overflow. But let's say we don't want to have an overflow and we want to have some mechanism by which we can store store the product without an overflow. So for this, let's do a little bit of math here. So as you see, the largest number that we can get by multiplying two signed numbers, two 32-bit signed numbers, is 2 raised to the power 62. If I consider two unsigned numbers, so basically the largest number that I can get, so in an unsigned number system with 32 bits, the largest number is 2 raised to the power 32 minus 1. So if I sort of square this, then this will be 2 to the power 64 minus 2 times plus 1. So we shall see that in both these cases, so this is signed multiplication where we consider them to be signed numbers. This is unsigned. So in any case, be it either signed or unsigned, 64 bits are sufficient to keep the product. "64 bits in this sense are sufficient." So for this purpose, ARM has two instructions, smul and umul. So smul is a signed multiplication where we actually multiply the third and fourth operands. We multiply R2 times R3. We do a signed multiplication. So we assume that R2 and R3 are signed and the final result is signed. So the 64-bit product is actually, it can't be saved in one register because it's a 32-bit register, but it can be saved in two registers. So the lower 32 bits can be saved in R0 and the more significant 32 bits can be saved in R1. So together we'll have a 64-bit quantity. So this is the smul instruction. Does this with 4 operands where we multiply the third and fourth operand, and the first and second operands together store one number, where R0 stores the lower 32 bits and R1 stores the upper 32 bits. So we have a similar instruction called umul, which is an unsigned multiplication. So this is, if you would see, this instruction and the upper instruction and lower instruction are exactly the same. The only difference is, instead of a signed multiplication, it's an unsigned multiplication. So we treat R2 and R3 also as unsigned quantities, and we perform an unsigned multiplication. So the final result will fit within 64 bits. The lower 32 bits can be saved in R0 and the upper 32 bits can be saved in R1. So the only difference between smul and umul is smul does a signed multiplication and umul does an unsigned multiplication. Now let us consider an example. So let us compute 12 cube plus 1 and save the result in R3. So let's do one thing, let's load the values. So load the values basically means transfer the values. So let's transfer 12 to R0 and let's transfer 1 to R1. So now let's perform the logical computations. In the ARM ISA, the @ symbol is used to specify that what lies after it is a comment. So let's first multiply R0 with R0, which is, let's compute 12 square and save it in R4. So R4 will contain 12 square. Now here is the greatness of the MLA instruction, multiply and accumulate. So here we compute R3 is R4 times R0 plus R1. R4 is already 12 square and R0 is 12. So this is 12 cube plus the value in R1 is 1. So we get 12 cube plus 1. So what we can see is that using the MLA instruction, computing 12 cube plus 1 actually became very simple, and we could actually do it in two assembly instructions after we had the values in the registers loaded. So this is actually very cheap and very fast. So the user should keep this in mind, that occasionally you should take a look at some of the advanced instructions that ARM provides, such as MLA, SML and UML, to make the computation easier and also reduce the lines of code, because in assembly language, lower is the lines of code, more efficient is the program. Now let's take a look at some of ARM's advanced instructions. So ARM has a notation of a shifter operand. So let's see what it is. So consider a register. So we can optionally specify after a register ID a shift amount. So there are four ways that we can actually shift a register in ARM. So it's a so LSL. So let me first explain what is there in this table. So LSL means logical shift left. So let me just write, or maybe I can write here. LSL is shift left. LSR is logical shift right. So this is similar to simple RISC. ASR is arithmetic shift right. So there is no arithmetic shift left, so that's the reason we have not defined it. So LSL is the same as the LSL in simple RISC, a logical shift left. And so then there are two kinds of right shifts. In a logical shift right, we add zeros to the MSB. And in arithmetic shift right, we replicate the sign bit. So given a register, we can add these three kinds of shifts to it. And also we have this ROR kind of shift. So we'll discuss what an ROR is when we come to this part of the figure, the lower part of the figure. And then we can shift a register either by a certain shift amount, which can be between anywhere between 0 and 31, or we can shift it by the amount written in a register, written in another register. So basically we can put in a register over here, or we can consider this immediate, which encodes the shift amount, how much we should shift it by. So let us consider a simple 5-bit example, and let's say we want to logically shift it left by one position. So in this case 0 will come here, so we'll have 0 1 1 0, which is essentially this part has come over here, 0 1 1 0, and we shift in a 0 in the LSB position. So this is a logical shift left. So in ARM, we'll see in the next few slides that it is possible to actually fold in the shift information as a part of the operand specification. So we don't need a separate shift instruction, but let's first appreciate the types of shifts in ARM first. Subsequently, we have an LSR. So in LSR, if you have 1011, so 1011 will again get replicated over here in 1011, and in the MSB position we will shift in a 0. Similarly, for the arithmetic shift right, the bits 1011 will get shifted to the right, and in the MSB position we will shift in a 1. The reason being that we are replicating the sign bit. The sign bit here is 1, so we are just replicating it as arithmetic shift right. Now let's introduce the rotate right instruction. So ROR is rotate right, So what we do in this case, if we want to rotate it right by one position, so rotate right is basically a right shift with the values that are falling off the least significant position, they come and sit in the most significant position. So let's see. Let's consider 1011. If you rotate it right, the first thing that we do is we shift it to the right by one position. So 1011 over here gets reflected over here. Subsequently, what do we write in the MSB? We write in the MSB whatever was shifted out of the least significant positions. In this case, 0 was shifted out. It sort of fell to the right. So essentially 0 comes and it is put in the MSB. So essentially we are taking a set of bits and we are just rotating them. So another important point is that in these shifting operations in LSL, LSR and ASR, we are actually introducing new bits which were not originally there in the set of bits, right, at either the left position or the right position. In comparison, in the case of a rotate instruction, we are not doing that. So whatever bits fall out of the least significant position are added to the most significant position. So now given that these four shift operations are clear, let's actually take a look at an example of this. So let us, without an example it won't have been clear. So let's consider the following example. So write ARM assembly code to compute R1 equals R2 by 4. So essentially dividing a number by 4, as was discussed in chapter 2, as same as right shifting it by 2 positions. But this is not a logical right shift, it's an arithmetic right shift. We'll call it an ASR. And we shift it by 2 positions. So in the case of the ARM ISA, we actually don't have shift instructions. So basically in the previous slide, what we have seen, LSL, LSR, ASR and ROR, they are essentially shift directives, but they are not. So the important distinction that needs to be made is that these are not separate instructions in their own right. So what we essentially do is that we use the move instruction and we are treating this entire new expression that we have not seen before as actually one operand. It is true that there is a comma in the middle, but this is actually being treated as one operand. And this is being moved over here. So what is this doing? What this is doing is that this expression is taking the value of R2 and right shifting it. So maybe I can write the right shifting it by 2 positions. So this, I'm using the standard right shift operator. So we are right shifting it by 2 positions, which is tantamount to, equivalent to, dividing the number by 4. And then this entire, the result of this is being transferred to R1. So as I said, let me just re-emphasize that ARM, most variants of ARM assembly, at least most of the simple variants, don't have dedicated shift instructions. Rather, the shift is folded into the definition of the source operand itself. So in the source operand, we can specify the source operand as a register. And this is not possible to do with an immediate, but as a register, we can specify the source operand and optionally specify a shift amount and the type of shift. So there will be a comma between the source register and the type of shift and the shift amount, but the entire ensemble is treated as a single operand. And what the hardware would do is it would first evaluate the value of this expression, which basically means shift R2 by 2 positions to the right and then transfer it to R1. So let's now take a look at a slightly more complicated example. So let's compute R1 equals R2 plus R3 times 4. So multiplying a number by 4 is the same as shifting it to the left by by 2 positions. So what we will do is we'll write add R1. So since the first operand is the destination, so we will have R1 is being set to. So here the entire operand is actually just one source operand, right? So we can treat this as a single source operand. So we'll add R1 as R2 plus R3 left shifted by 2 positions or multiplied by 4. It's the same thing. So we'll have R1 is R2 plus 4 times R3, which has been folded into one single assembly statement, and this will make the execution of the assembly statement extremely efficient. So the important point to note is that ARM does not have separate shift instructions. Rather, a shift is folded in to the definition of the operand itself, to the specification of the operand itself. Now let's take a look at compare instructions. So they work very, in a very similar fashion as simple RISC. So a compare instruction, it does the job of comparing, and then it sets the flags. So let's first take a look at a simple compare instruction with a CMP instruction. We had a CMP in simple RISC as well, and the format was the same. The first operand was a register. The second operand was either a register or an immediate. So we are comparing R1 and R2. And after this, so what does comparing R1 and R2 mean? It essentially means that we subtract R2 from R1. So we compute R1 minus R2, and we set the flags after computing R1 minus R2. So in simple RISC, we had a flags register. In ARM, it is called the CPSR register. It's the same as what was flags in simple RISC. So this is a CPSR register. The CPSR register is called the current program status register, which does not have one flag, it has 4 flags. So the first flag is negative. So negative indicates that when I did R1 minus R2, R1 was less than R2. So in this case, the negative flag will be equal to 1. Then we have the 0 flag, which means if R1 was equal to same as R2, then the 0 flag will be equal to 1 and the negative flag will be equal to 0. In the carry flag is basically done to indicate that I did an addition and after that a carry was generated. And similarly, the overflow flag is set to indicate that the result exceeded the range of the number system. As a result, it cannot be saved, and so the programmer should be told that look, the addition or multiplication that you are trying to do exceeded the range of the number system, and as a result there has been an overflow. So here is an important point that we should need to note. It is slightly non-intuitive, so that's the reason I'm putting a big arrow to its left. If we need to borrow a bit in a subtraction, so carry is mainly used in the context of addition, but we need to borrow a bit as is in the case of subtraction, then we set the carry flag to 0, right? So the moment we need to borrow, we set the carry flag to 0, and if we do not need to borrow a bit, we set it to 1. So this is slightly tricky and non-intuitive, so let me repeat it once again what I just said. What I said is that if we need to borrow a bit in a subtraction, so we subtract 2 numbers and it's necessary to borrow, we will set the carry flag to 0. For example, if we are subtracting 0 minus 5, so this, if I write in binary, it is essentially 0 minus, right? So in this case, when I'm actually subtracting, there is a need to actually borrow bits. So in this case, the carry flag will be set to 0. Otherwise, it will be set to 1. So similar to the compare instruction, we have a CMN which is actually called compare negative. Format is the same, but instead of actually setting the flags after computing R1 minus R2, we compute R1 plus R2. Or this is the same as, you can think of this CMN R1 R2 is essentially equivalent to compare R1 with minus 1 times R2, right? So that's the reason it's called compare negative, where instead of comparing R1 with R2, we are comparing R1 with minus 1 times R2. Similarly, we have the test TST instruction. So we set the flags after computing R1 and R2. So if R1 and R2, if the final result is 0, we'll set the 0 flag, or we'll essentially take a look at the final result, and based on that we'll set the flags. So let's say the final result, the MSP is 1, we'll set the negative flag, and so on. So TEQ basically tests if so what we do is we compute an XOR of R1 and R2. So we set the flags after computing R1 XOR R2, and we take a look at the result. If the result is all zeros, we'll set the 0 flag. Otherwise, if the result has a positive sign bit, we'll set the negative flag. So TST, TEQ, and CMN are typically not very commonly used, even though you can use them if the situation so demands, and if you feel that we can reduce the number of instructions by using these flags. So the ultimate reference for any kind of ARM instruction is the ARM instruction reference manual, which you can get on ARM's website. So there you will find a lot of these concepts explained in great detail. So the reason that I'm not going into more depth is basically because some of them have many cases and subcases. So this is better dealt with in a manual which describes all the cases in great detail. So we, for most of our work, will only stick to the compare flag. The compare instruction. And the compare instruction will tell us using the negative and 0 flags, which is very similar to what we had in simple RISC. To basically the 0 flag was the equality flag, and if R1 was greater than R2, we're setting the GT flag. So in this case, the flags are different, but the connotation is similar. So we'll use mainly the compare instruction to do our job. So now ARM has some more interesting instructions. So the compare instructions are not the only instructions that set the flags, right? So in simple RISC, CMP was the only instruction that was setting the flags, but in ARM that is not the case. So you can add an S suffix to regular ALU instructions such that they will set the flag. So an instruction with the S suffix will set the flags in the CPSR register. For example, if I, let's say, add two numbers, so I can replace the add instruction with an add S instruction. So the add S or the sub S instructions will actually set the flags. So they will perform the addition or the subtraction, and subsequently, based on the result, they will set the flags, whether the number is negative or 0, or if the addition led to an overflow. So all of these conditions can be set. Now let's take a look at a set of very interesting instructions that actually use the flags. So the first instruction that we'll look at is ADC. The ADC is an add with carry instruction. So in this case, we do add with carry is R1 equals R2 plus R3 plus the carry flag. Right, so if there is some previous carry, so this ADC instruction, you'll find an example in the book that uses it, but essentially the idea is that if previously a carry was generated, then we can sort of use the carry. So basically we will add R2 and R3 similar to the add instruction, and also add the carry. Similarly, we have a SBC instruction subtract with carry, which first subtracts R2 minus R3 and then it subtracts it with the NOT of the carry flag. So this is slightly tricky. So what did we say? Let's go back to the slide that talked about the borrow bit. So if we need to borrow a bit in a subtraction, we set carry to 0. Otherwise, we set it to 1. So in this case, in the previous subtraction, if it led to a borrow, the carry flag is 0. So NOT of the carry flag is actually 1. So what we do is that this is sort of giving effect to a borrow or implementing a borrow. We do the regular subtraction and then we subtract a NOT of the carry flag, and the NOT of the carry bit can be considered the borrow bit because their connotations are exactly reverse. So you will find an example in the book where we use the ADC and the SBC instructions to actually subtract large 64-bit or even larger quantities. The RSC instruction is similar to RSB where we do a reverse subtract, but in this case we do a reverse subtract, which is R3 minus R2, R3 minus R2, but we also subtract the borrow bit, which is the NOT of the carry flag from this. So here is one example that will show you the power of what the carry flag and the add S and ADC instructions do. So this typically I used to set as an exam question, and I asked to use students to do this in simple risk. So this was fairly difficult and it used to take a lot of lines because simple risk didn't have the support to do it. So what do we want to do? We want to do 64-bit addition using 32-bit integers. So consider the SMUL and the UMUL instructions. So they save the result in a pair of registers. So let's assume that this is the case. Let's assume that a 64-bit value, which is also called a long value, is stored in registers R2 and R1. So R1 contains the lower 32 bits and R2 contains the upper 32 bits. Similarly, we have another register pair R4 and R3, where R3 contains the lower 32 bits and R4 contains the upper 32 bits, and together they make a large 64-bit number. See, we want to add these pair of numbers, these long numbers, and also save them in two registers R5 and R6. So what we do is first, so let's say the numbers are of this form R2, R1 and R4, R3. You want to add them. So the first thing that can be done is we can add R1 and R3 and save the result in R5, which is exactly being done over here. But note the S suffix with the add instruction. The S suffix is basically telling the add instruction that look, you go and set the flags. So here, which flag are we interested in? We are interested in only a single flag, which is actually the carry flag. So what is happening is that if the carry bit is set, we need to record this fact, and this is being recorded in the flags, that if there is a 1-bit carry, this needs to be recorded. Subsequently, we add R2 and R4, but we use the ADC instruction because this adds R2 and R4 plus the carry. So that's a very important thing. It also takes the carry into account, which might have been generated. It adds R2, R4 and the carry and saves the result in R6. Right, so what is written is that the add-s instruction adds the values in R1, R3. ADC add with carry adds R2, R4 and the value of the carry flag, which is exactly the same as normal addition. Had add-s and ADC not been there, it would have been fairly difficult for us to achieve this task. And so consider a program that has a lot of SMUL or UMUL instructions, and they produce 64-bit outputs. To manage the 64-bit outputs with to manage them and add and subtract them would have been very difficult had we not had this particular mechanism. So given the fact that we have seen this, actually let me go back to the previous slide. Given the fact that we have taken a look at 64-bit addition, I would request the readers to also look at 64-bit subtraction. So in the case of a 64-bit subtraction, the idea is very simple. We do exactly this. So we will have exactly the same thing, and instead of an addition we'll have a subtraction. So first, instead of an add s, so let me just give a hint, but I'll not tell you the entire solution. So we can, instead of an add s, we can have a sub s. We can write something, and subsequently we need to go back to our set of instructions and use the SBC instruction. The SBC instruction will subtract with carry, which will take the borrow into account, and we can do something and also achieve subtraction in 64-bit subtraction in 2 instructions.